Alright, y'all, welcome to the video key for the thermochemistry take-home test. We've got some extra credit in here, so make sure you're watching all of it to check your answers and get those points. You can pause it if you want to check your answers. We did this at a lab station in class, so hopefully you have your word bank for that. Otherwise, I wanted to jump down and start talking about 3. Okay? So we're looking at, circle all of the examples of matter below and underline all the examples of energy. We said matter is anything that has mass and takes up space. Alright? So basically, anything on the periodic table is matter. If it's made of oxygen or aluminum or protons or those have mass, they take up space, they matter. So in this case, light, definitely not on the periodic table. That's just a form of energy. Radio waves, form of energy. Heat is a form of energy. Oxygen on the periodic table, it has a mass of 15.999 grams per mole. Definitely has a mass. Electrons, we said in class, electrons are like earrings. They're little compared to the rest of your body, but they do have mass and they do take up space. An atom, protons, electrons, neutrons, that has mass and takes up space. Protons have mass and take up space. Sound does not. That's a pattern of movement through matter, but it's just a form of energy. My desk is mostly made of carbon and some other silicates and whatnot. That's going to be matter. Air, like oxygen or carbon dioxide or nitrogen. Again, if it's made of stuff in the periodic table, or protons, electrons, neutrons, those would all be considered matter. These 4 are my energies. I'm not going to write a sentence for you, 1 to 2 complete sentences, but I am going to remind you that entropy is that random word that means random. Okay? So entropy is a measure of disorder and randomness. So a gas is more random than a solid, or has more entropy than a solid. So that's what I wanted to talk to you about on number 5. Compared to solids and liquids, gases usually have blank entropy and are blank organized. Okay? So if entropy is random, okay, gases usually are more random or less random. We would say they're more random. Okay? Solids are sitting still. Gases are definitely going to be more random. In our notes, we had this particle diagram showing you that a solid forms this pattern. Gases are less dense and more random. So I want to get rid of these ones, A and B again, because it's definitely not going to be less random. And then we want to say, and are blank organized. Well, if you're more random, that means you are less organized. So this is going to be the one we want to pick. More random, more entropy, and less organized. Okay, this is going to be our first extra credit. If you go ahead and copy this down, and then write +2 extra credits. Okay, so what this is showing you is solid to liquid to gas. So going from a solid to liquid would be melting, liquid to gas, evaporating. Going in this direction from solid to liquid or liquid to gas is always, and you know what, I used the wrong color there, but that would be endothermic. Okay, and going from a gas to a liquid and a liquid to a solid is always going to be exothermic. Okay, the reason for that, if you don't remember from class, is gases move quickly. They have a lot of kinetic energy. Solids are slow. So in order to speed up from a solid, slow solid, to a medium liquid to a fast gas, going this direction, you have to take in energy. Energy is going into that material in order to get it hyper. It needs to take in some caffeine or something. In order to go from a wild hyper gas to a more calm liquid to a sitting in my seat solid, you have to let your energy out, exothermic. Okay, and we did that in class where we froze the liquid hand warmer and it felt really hot. Okay, so when solid ice melts, it has more or less entropy as a liquid than it did a solid. Well, melting, going from solid to liquid, would be endothermic, and it's also going to be more random. Okay, it has more randomness, more entropy. All right, let's turn over and look at page 2. You should have had this done from class, and I'm also going to label these points. That should have been labeled from our lab activity in class. Okay, but this is your final energy and your starting energy. I won't label all of that because you should have done it, but let's look here. Number 9, what's the equation for finding enthalpy, or this triangle H, delta H of a curve? Okay, so the equation is to take your final energy minus your starting energy. So you can write that, say final minus initial. But if we want to be a little more science nerdy, because we are, the more accurate way to say that would be taking your products, okay, taking the energy of your products, which is what that is, minus the energy of your reactants. Okay, so it's a good idea to know both of those things. I'm not going to do 10, 11, and 12 with you, but that will be done very similarly to how you should do 13, 14, 15. We're going to look at that together. So looking at these two different kind of heat diagrams or energy diagrams, we've got one that ends up higher and one that ends down lower. And my students like to memorize that if you're writing a cursive X, okay, this is the graph for exothermic. So just by looking at this one, I have students that would be like, oh, that's an X, so I know that that one's going to be exothermic. And you can just put exothermic. Really, the better way to know that that's exothermic would be talking about energy. So this is my energy at the beginning of the reaction. I activate it, and then at the end of the reaction, I have less energy. So if this is your bank account, at the end of the day, money went out, or energy went out. And so here's some more extra credit. If energy goes out, it's exothermic and would feel hot. Okay. So go ahead and copy that down and put +2 extra credits. Okay. So overall, this is exothermic because, how do I know? Energy, E-N-E-R-G-Y, I think I got lost, is decreasing. And I'm going to put going out in parentheses. Okay. So what is the overall enthalpy change, delta H, of this reaction? Just like I said up here, I want to take the product minus the reactant. So I want to take this product energy minus this one. And it looks like it's ending at about, I don't know, what we call that, 18. Okay. So let's say my final energy is 18 minus, I'm starting at, looks like not quite halfway, so maybe 50. You could probably say 52. Okay, you don't have to be super precise on this graph. So I'm going to say 18, my final product, minus my starting energy, 52, equals about negative 34. And be very careful about the positive negative. And think about it. It's coming down in energy by 34 or 35. Okay? It's coming down in energy, so that's why it's negative 34. Activation energy, I showed my students in class that it's always A+, activation energy. It's how much higher do you have to get, but activation energy has to be positive. So I'm going to take my highest point minus my starting point. So my highest point looks like it's about 80. 80 minus my starting point, about 52 or 50 or 55. Okay, and I would say 80 minus 52 equals positive 28. Because it's coming up by about 28. That's how much energy it takes to activate this reaction. So that's going to be very similar to how you should go back and look at this graph. Okay. Turn over to page 3 with me. I already have my number 16 labeled. This is the way you should have labeled it at your group. So if your group was wrong, make sure you're fixing it. I want to point out that wherever your line is sloped, that's where you have a temperature increase, and it's where you have just solid here, just liquid there, just a gas there. And then, going from a liquid to a gas is boiling. Going from a gas to a liquid is condensing. Going from a solid here to a liquid is melting, and then back to freezing. Okay. You have to know how to label that on your own, so make sure you're making flashcards or something if you need to. But that's how you should have had 16 labels from your lab if you did it correctly. Looking at 19 and 20. Okay, it says water would be a boiling or evaporating as you move from points blank and blank. So boiling, I have that labeled. Boiling is going from a liquid to a gas. Boiling or evaporating. So that would be going from point 4 to point 5. That's where it's boiling. No matter how fast, aloha, no matter how fast it boils, it doesn't boil hotter. So that is going to be fantastic new extra credit. If you get it, good, but put +2 extra credit. If you write the word aloha right there, A-L-O-A-H-A, I think I spelled that wrong. Now I need to even fix my least favorite word of all. Oh, come on. Aloha. There, now it's an H. And give me a big old smiley face, too. Alright. Question 20 says, what's happening to temperature as you move from point 4 to point 5? Okay, temperature is this axis. And if you look at 4 to 5, there is no slope there, which means that axis is not changing. So what is happening to temperature? You're going to say it's constant, or no change. Okay, and the reason for that is even though I'm putting in heat to it, that heat or that energy is being used to change states. So temperature is not changing, but it's a state change there. So all of the energy is being used to take those liquid molecules and turn them into gas molecules. So that's why it's constant there. For these multiple choice ones down at the bottom, we're looking at reminding you if it's false, you have to correct the statement to make it true. So if it's true, you can move on. If you say false, you have to go back and fix it. So let's look at 23. 23 says, true or false, the enthalpy change, delta H, of a reaction is determined by taking the energy of the reactants minus the products. Okay, and we just answered that over here. We said products minus reactants. So we're going to go ahead and say, uh-oh, this is false. And in order to correct it, I'm going to circle this as the problem and say should be products minus the reactants. Okay, so it's the end minus the start. Okay, that's how you know how you changed. Question 24 says, cooking pancakes with direct contact on a pan would be considered convection. That's going to be false. When they're touching, so I'm going to say contact equals conduction. Okay, that would be considered conduction because they're touching. Okay, do some of those other ones on your own. Check your notes. Number 28. In order for a gold bar to melt, energy must be absorbed, making it endothermic. I'm going to come back to page 1 where we put that extra credit right here, okay? So melting is going from a solid to a liquid. And we said that's going from slow to medium speed. This direction is endothermic. So in order for it to melt, energy must be absorbed, making it endothermic. True. Energy has to go into it in order to speed up and melt. 29. A material's freezing point equals its boiling point. The answer to that is up here. We labeled it. Okay? It freezes and melts at the same temperature. It boils and condenses at the same temperature. But it definitely does not freeze and boil at the same temperature. So I'm going to say false. And I'm going to change its boiling points to its melting points. Now it's true. I'll help you out with a couple of these other ones too if you're checking your work. Okay, this first one should be true. This one should be false. Make sure you're fixing that one. Okay, then do those middle ones on your own. Page 4, we've got our other kind of graph. It's called a phase diagram. Okay, you should have labeled this at the lab table in class. And you do need to know that this area is solids, the middle area is liquids, this area is gas, and that is called the triple point. So make sure you're memorizing that. Okay, I wanted to, even though I didn't highlight it, let's start by looking at 34 here. It says a sample at a pressure of 1.5 atm. So I'm going to come over here to 1.5 atm and kind of draw a line. And a temperature of 600. I'm going to go like this, straight up. So there's the point. Would be in what phase? That falls into the liquid area. Everything in here would be considered a liquid. So I'm going to say A, liquid. Number 35, using the sample from the previous question, which is this point right here, if the pressure is decreased to 0.75 atm, so if I drop this down at the same temperature but down to here, okay, what phase change will occur? So that means my point is going from the liquid area to the gas area. And a liquid turning into a gas is evaporating. So I'd say that's evaporation. Okay. Take a look at 36. Assume a substance is at a pressure of 1 atm. So that's going to be right here. I'm going to switch colors. And a 200 degrees. Okay, so that combination of pressure and temperature would be liquid. If the temperature is lowered to 0 degrees, so if I move it, the pressure is not changing, but I'm taking this point and I'm moving it here, what state would it change to? Well, now it's not in the liquid area, that point's in the solid area, so I'm going to say solid. And what is the name of that phase change? A liquid turning into a solid, like water turning into ice, that's freezing. Okay, so if you know solid, liquid, gas, and you know what it's called going between those areas, that's how we answer these types. Let's look at some of our delta T's. Okay, 38 and 39. Here's going to be our next little extra credit. Put +2 extra credit if you write this down. Okay, and that's going to be delta T equals TF minus TI. Okay, so if you write that, you get your other 2 points of extra credit. So the change in temperature is your second final temperature minus your first initial temperature. So looking, it's asking me to find change in temperature, and it's giving me this one and this one. So I'm going from this, TI, to this, TF. So I'm going to say 80 minus 0 equals 80 degrees Celsius. And that's positive because it's warming up. For this one, calculate the change in temperature when lead is increased from this temperature to this temperature. So I'm going to say 60, my second temperature, minus my starting temperature equals 19 degrees Celsius. And again, that's going to be positive 19 because it's heating up. Okay. All right. Finish this page on your own if you haven't. And turn over to page 5. This is where we've got our math. I'm not going to do 41 with y'all because hopefully you did that with your group, but I would like to do these last 4 together. Okay, and I'm going to grab a periodic table here. Let's see. Here's my periodic table. It's got my equation here. That heat, gained or lost, equals mass, times specific heat times the change in temperature. So Q equals M, mass, times C, specific heat, times delta T, change in temperature. Okay. Box in your givens and circle your unknown, and that's going to be your last extra credit points. I'm going to set +2 extra credit if you do this. Given and unknown. Circle it. Okay, so I'm going to use green for that. The temperature of a sample of iron increases from, here's a given, as it absorbs this much heat. What is the mass of the sample? That's what they're asking me. And they tell me the specific heat of iron is 0.450 joules per gram degree Celsius. Okay, so I have boxed in my unknown, and now I'm going to go back and label it. Okay, that this is a temperature and this is a temperature. This is my initial starting temperature and this is my final temperature. It absorbs this much heat. Okay, heat is what's in front, and Q is what's in front there. So I'm going to call this Q. It's asking me to find mass, which is M, and it tells me specific heat, which on here specific heat is in the middle, and C is in the middle. So the variable for specific heat is C. Okay. So if we're doing our guess, given unknown equation, I'm going to say Q equals MC delta T. That's the equation I'm going to pick. I'm going to use a different color for M, because that's what I'm solving for. And then substitute. So my Q, 2,184, equals mass, and I don't know what that is, so I'm going to leave that as X. That's what I'm solving for. Times C, which I labeled as 0.450, and then delta T, I need to find the change in temperature. So I'm going to take my final second temperature of 98.8 minus my starting temperature, 34.1, equals, let me grab my calculator for that. 98.8 minus 34.1 is 64.7. And I got a positive 64.7, which it should be, because my change in temperature is increasing, it's positive. So 64.7. Okay, the algebra for this now is to combine like terms. So I want to do that math, I want to multiply those. 0.450 times 64.7 equals. So now I have X times 29.115 equals still my Q, 2,184. Okay, I've combined like terms, and now I'm going to divide both sides. So instead of X times 29, I need to cancel that out by divided by 29. And I do that to the side too, 29.115. So when I do that, 2,184 divided by 29.115, I get my X of 75.01. And if we're talking about significant figures, this would be rounded to 3. So 75.0, and it's asking me mass, so grams. Notice how that's a positive number. You can never have a negative mass. Okay, it should always be a positive mass if you're solving for that. Okay. Question 44, we're going to box and circle. For a chemistry lab, a student needs to calculate the heat gained or lost by heating some magnesium. The student heated 7.5 grams, there's my mass, of magnesium with a specific heat of, so there's my C. The initial temperature was, so there's my TI, and the final temperature was 124, TF. How much heat was gained or lost? So heat gained or lost, that's the first one on my equation list, which means Q is what I'm solving for here. So givens identified, unknowns identified, equation. I'm going to say Q equals MC delta T. I'm going to substitute. For my Q, I don't know what that is. That's what I'm solving for. So I'm going to say X is what I'm going to substitute in for Q. Mass is the grams, so they tell me 7.5, times C, the specific heat of 1.02, times change in temperature. I still need to calculate that. So my change in temperature is my final temperature of 124 minus my starting temperature of 34, which should be 90, but watch me do that wrong. 124 minus 34. Oops. 124 minus 34. 90. Just making sure. And again, it's increasing the temperature, so my change should be positive 90. Okay. Now, unlike 43, there's no algebra to do. Here my x wasn't alone, so I had to do some crazy algebra. Here my x is alone, so I just do the math. This times this times this. Sweet. So this is the easier problem for sure. 7.5 times 1.02 times 90 equals 688.5. We would round that for significant figures, but we don't have to worry about that. And heat gained or lost is in the unit joules. And that's positive. Okay, so that's how to do the algebra. Please go back and watch the video tutorial for pages, I think it was 6 and 7 in the homework if you need more help with this kind of math. And then let's look at it conceptually. So last thing we need to take a look at. Okay, so I'm giving you this. You're on vacation in Hawaii because you're way more lucky than me. So it's a hot sunny day out. Using this table, what surface will heat up fastest in the sun? So water with a specific heat of 4.18, sand with 0.19, cement 0.39, wood 0.41. Okay, so we learned in class that small specific heat is easy to change. That's why sand gets so hot at the beach, because it only has to take a little bit of energy, joules, to make 1 gram 1 degree hotter. So sand is going to heat up first. It's also going to get cooler first. So using this table, what surface will heat up fastest in the sun? I would say the sand. How do I know? Because it's the smallest specific heat. Okay, you're on a vacation in Hawaii still, lucky. At night, what surface will stay the warmest the longest? So we just said sand, it's very easy to heat it up, and it's very easy for it to lose that and cool back down. Which one's going to stay hot the longest is going to be the biggest specific heat, water. Okay, so it takes our oceans and our water a long time to heat up, but once they are warmer, they stay warmer longer. So I would say the water, because big specific heats it's hard to change. Okay, hopefully you found all 10 points of extra credit. Good luck, y'all.